Hello everyone, I'm Krishna Subramanian and I'm presenting this paper on behalf of my co-authors Johannes Maas and Jan Borchers. All of us are from the RWTH Aachen University, Germany. I'd like to discuss with you our attempts to understand and support source code experimentation in hypothesis-driven data science. This presentation is divided into three sections. First, we'll have a look at the motivation behind our work, which is largely influenced by a formative study that we did. Based on the study, we built a tool called TRACTUS. This will be the second section of the presentation. And finally, we will discuss the results of the evaluation of TRACTUS. So first, let's have a look at what hypothesis-driven data science is. Let's imagine we are analyzing a data set of book sales. So this data set consists of information like the number of pages, the genre of the book, and also information about how many copies were sold and the details of the buyers. So the buyer's age, the buyer's gender, and so on and so forth. So after loading the data and using visualizations and descriptive statistics to understand the data, we may come up with one or more hypotheses. For example, are more copies of fiction books sold than non-fiction books? Are women more likely to buy books than men? And so on. To validate each of these hypotheses, we need to go through a series of steps. For example, we may have to do some data preprocessing, format the data, we use summary statistics, perform assumption tests, and so on. At each step of this analysis, crucial decisions are made that influence the rest of the analysis. For example, if we discover that our distributions are not normally distributed, we might try to transform the data or perform a non-parametric test. Also, it is important to note that not all validations might pan out. Sometimes we may have to drop a hypothesis and move on to the next one. During this experimentation phase, the data scientist generates a lot of key insights. Also, he or she makes decisions about the analysis technique that she uses. And these rationale are very important and needs to be documented later on as a form of a report, a paper manuscript, or in a production quality code. Also, source code from the experimentation phase will also be moved from the experiments to production quality code in a selective manner. In order to understand how data scientists currently get from experimentation to writing production quality code or reports, we conducted an observational study with 10 academic data scientists. All of our participants had experience with R, a very common programming language for data science, and they came from different fields like numerical analysis, applied psychology, and human-computer interaction. We collected around 8 hours of video footage and used qualitative coding techniques to understand our participants' coding, documentation, as well as their analysis behavior. I'd like to discuss just a couple of our key findings now. First, unsurprisingly, we found that hypotheses are the building blocks of analysis. Hypothesis is the hero of each and every analysis, and it is the concept around which our participants structured their analysis. But more interestingly, we found that the source code that our participants wrote to conduct the hypothesis testing, hypothesis validation, usually consisted of some syntactic signals that indicated what hypothesis is being validated. For example, here we have our code that is used for visualizing data from the book sales dataset that we looked at before. Specifically, we are plotting 3 histograms and a box plot, all of it to try and understand how many copies of books are sold from the different, how many copies of books from different genres, like fantasy, nonfiction, and horror were sold. The generic form of data selection operations looks something like this, and the generic form of data manipulation operations like subset looks something like this. So as you can see, this is a very reliable way to understand what is the current dependent variable and the independent variable in the hypothesis. Now let's look at the last line of code. This line of code uses what's called the formula notation in R, which is a very common notation used throughout R in functions like boxplot, which is shown over here, but also in many significance tests. And this essentially indicates that we are comparing the effect of the independent variable, in our case, the different genres of books, on the dependent variable or the measurement, which is the number of copies that are sold. This formula notation is really powerful and can be used to model a wide range of relationships. We mentioned earlier that after experimentation, data scientists need to recall the key insights as well as the rationale to be included in the report or the production code. In our study, we found that this is not so easy for our participants. Some of our participants had not captured any of their experiment code into a script file. So they had to rewrite code pretty much from scratch, and they had a lot of difficulty in finding the experimental code that they had written. Let's take a look at an example. Here we have participant 7 who has done most of his experiments in console, which is a very common behavior we observed among our participants. And now, once the analysis is pretty much done, he's trying to rewrite code from scratch into a script file. And when he's doing this, he oftentimes had to scroll through the console window to try and locate the right piece of code, as well as the execution output, to then capture into the R script. So eventually he finds the piece of code and the output and then moves it into the R script file. While the other participants did not have to rewrite code from scratch because they had captured the code in one form or the other, they nevertheless had to re-execute code, often several times, to be able to recall the key insights and the rationale. We further looked into what information or what hooks our participants were looking for when they were navigating through their previous experiments. We found 3. Before we try to look at the different hooks, let's first have a look at the source code. So this is a continuation of the source code we looked at before, where we are trying to understand the effect of different book genres on the number of copies of the books that were sold. So here we can immediately see that the code is organized into blocks. A block is usually one step of the analysis and is usually prefixed with a block comment. The block comments are high-level descriptions of what the block does. In addition to the block comments, we also have tail comments, which, while sometimes can be used for descriptions, they can also be used to describe what is programmatically done with the source code. Our second hook was the variables. So the names of the variables usually indicated what the variable is used for and help the participants understand and navigate their experiments. For example, over here, book sales refers to the data set, and M refers to the model that is built using the analysis of variance. And finally, participants were also looking at the execution output of their source code. This is not so surprising because the output usually contains the key insights that were identified during the analysis. So to summarize, the 2 main findings of our analysis are as follows. First, hypothesis is the hero of the analysis. The analysis code is organized around it, and code has syntactic signals that indicate the hypothesis. Second, hooks, which are contextual information like comments, execution output, and variable names, are useful for the data scientists when they have to navigate through their experiments. Based on these findings, we felt that we could support the data scientist workflow in a better manner. For this purpose, we developed a tool called TRACTUS. TRACTUS is an add-in for the RStudio IDE, which is a very common IDE for R. So here we have the RStudio IDE. On the left-hand side, we have an R script that the user is currently working on. And on the right-hand side, we have TRACTUS. So as you can see, TRACTUS visualizes the source code that the user is currently working on. Because hypothesis is the hero of the analysis, TRACTUS can group the source code into the corresponding hypothesis that they were used to validate. So you can notice that even though in the R script file, the source code is disjointed, TRACTUS is able to group them together in the visualization. And second, because hooks from previous experiments are really useful later on when writing production quality code and reports, TRACTUS is able to capture these hooks and visualize them in the visualization on the right-hand side. So here we have the different block comments, And here we have the different variable names that are used in the analysis, and other information like the tail comments and more information about the source code can be obtained by hovering over each line of code. So when you hover over the line of code, you get to see the execution output as well as any tail comments that the source code might have had. In the final section of this presentation, I would like to discuss the evaluation of TRACTUS. To evaluate TRACTUS, we had 7 participants take part in a study. Participants were given the task of analyzing 2 datasets. And since we wanted to understand how TRACTUS is used across the entire data science workflow, we asked our participants to use descriptive statistics and visualizations to understand the data and come up with hypotheses, and then use RStudio with the TRACTUS add-in to be able to validate these hypotheses. And once the validations were done, participants were asked to write a report based on what they did. We captured the video of the session and also collected qualitative feedback from our participants. Here we discuss a couple of findings. First, participants mentioned that they were able to compare parts of their analysis to understand the similarities and differences quite easily using TRACTUS. And some mentioned that it was very useful when writing reports later on. Here we have an example screenshot from TRACTUS. You can see 2 different hypotheses being validated here, and just by quickly looking at it, you can immediately spot a few things. For example, you can see that although both the hypotheses have been validated by using test for normality and test for homoscedasticity of variance, you can see that in this hypothesis, the user chose to do an ANOVA, which is a parametric test. This probably indicates that the distributions are normal and that the homoscedasticity assumption has been satisfied. But over here, the Wilcoxon test is used, which is a non-parametric test, which indicates that the assumption test probably failed. One of the unexpected benefits of TRACTUS is that it encouraged our participants to curate their code by improving their code awareness. For example, a couple of participants removed scratchpad code to clean up the visualization. The visualization over here shows scratchpad code usually done to test the library API, and you can see clearly that this is in its own branch, clearly separated from the main hypothesis that the user is testing. So we had a couple of instances where participants removed these instances just to clean up the visualization. We also had 3 participants who refactored their code, for example, by renaming variables based on the visualization that TRACTUS provided. TRACTUS does suffer from a few limitations. The participants in our formative study are all from academia, so our findings may not generalize to data scientists everywhere. Second, we conducted our observation only for a limited period of time. In reality, analysis can span multiple weeks and across several files. And finally, our parser suffers from some technical limitations. It does not parse all source code. It currently has a success rate of 82%, which we tested with a test corpus made up of real-world R scripts. And tail comments and graphic output are currently not captured, and files with syntax errors are currently not supported. However, these can be integrated into the parser later. To summarize, we looked at the data scientist workflow when analyzing datasets and validating hypotheses. And based on our observational study, we identified that hypothesis is the hero and that the source code contains syntactic signals that indicate what hypothesis is being tested. We also looked at the concept of hooks, which are contextual information like execution output, comments, and variable names, which are really useful to the data scientists when they are writing reports and production code. Based on our findings to improve the data science workflow, we presented TRACTUS. TRACTUS captures the source code and groups them based on the hypothesis that is being tested, and also captures and visualizes the hooks or the contextual information. TRACTUS is open source and you can download it from this URL. In summary, data scientists require some form of scaffolding to be more oriented in their analysis, and such scaffolding can help them greatly improve their workflow.